Previously I've shown these fuel-air burns, one of butane and air, similar to what powers your car, and the other one hydrogen and air, which is similar to the reaction, albeit in liquidized form, which powers the space shuttle. However, in those videos the bottles were open such that the hot expanding gases could produce thrust. And so comes the obvious question, what would happen if the bottles were not open? Now the interesting thing about gases is that at constant pressure, say for instance 1 atmosphere, and at constant temperature, say for instance room temperature, is that a constant number of molecules occupies the same volume. That is, 1 billion molecules of hydrogen will occupy about the same volume as 1 billion molecules of oxygen. Now if you increase the number of molecules in a volume, say for instance by a chemical reaction, you increase the pressure, and the higher the pressure, the better the thrust you can generate from it. Now the bizarre thing about the hydrogen-oxygen burn though, is it actually decreases the number of molecules of gas. That is, you start with 3 molecules of gas and you end with 2 molecules of steam. And yet hydrogen-oxygen is still one of the most effective rocket fuels available. So how is this possible? Well, when these gases burn they get hot, and that causes them to expand, or in a confined system, it causes the pressure to increase. So how hot does a hydrogen-oxygen burn get? Well, if we take absolute zero over here, that's basically when all the molecules are stationary, and the surface of the sun over here, that's about 6,000 degrees Kelvin, or degrees Celsius, it really doesn't matter at this point. Well, it turns out that the hydrogen-oxygen burn, or adiabatic flame temperature as it's more appropriately known, is about 3,000 degrees Kelvin. That's about half the temperature of the surface of the sun, and I'm going to put that in a pop bottle. Now, if you increase a gas's temperature from, say, 300 degrees Kelvin, that's room temperature, to 3,000 degrees Kelvin, in a confined system, you will increase its pressure by a factor of 10, that's from 1 to 10 atmospheres. That's getting close to the failure threshold of these standard polyethylene terephthalate pop bottles. Now in absolute terms, the energies involved here are not that big. What I'm going to do is turn about half a gram of water into hydrogen and oxygen and then burn it. And given that all chemical explosives have comparable energy content per unit mass, the energy in this explosion will be about equal to 1/10 of the explosive charge used in a typical bullet. Now I'm going to generate all of that energy from this. And in fact, yeah, this is the exact self-same battery that I jump-started my car from about a year ago. Now, there's actually nothing special about this battery, it's just a standard 3-cell lithium-ion polymer battery, similar to the things that run virtually all of the cell phones and laptops today. I'm just going to use this so you can visualize the energy content of many everyday objects. Energy, remember, is conserved, so the 3,000 degree fireball that I'm going to generate, all of that energy resides within pretty much the battery of every laptop on Earth today. The absolute energy yields here aren't actually that great. I mean, it's the form and rate that the energy comes in that are hazards here. For example, the energy released from the lighter fuel you might use to start a barbecue may well be about 100 times the energy content that you would get out of a bullet. But the fact that the bullet delivers its energy locally and in milliseconds is what makes it more dangerous. It's for this reason that I've, for my own safety, put a plexiglass screen between me and the hazard, and I've also taken the precaution of earplugs, given that ears are really quite sensitive to this sort of thing. And for those who think that you can be cavalier with such systems, I present this. This is what it looks like when you get idiots who don't know what they're doing, fooling around with high-pressure, confined systems. Now, it's not entirely clear what happened to this guy, other than it happened in less than a frame on the video. That's about 30 milliseconds. If he was lucky, the rupture basically fired the bottle out of his hand, and the blast was focused downwards or away from him, and the chemical cloud did not get in his eyes. If he was unlucky, the rupturing pop bottle could have severely lacerated his fingers. The local 10-atmosphere pressure wave so close to an open ear could have caused hearing damage, and the corrosive chemicals they used to generate the pressure would have sprayed into his eyes, possibly damaging them. 30 milliseconds and a little too much youthful exuberance and not enough experience can generate a lifetime of regret. And yep, on paper, my pop bottle of hydrogen and oxygen contains a comparable amount of energy. However, with the use of earplugs and a plexiglass screen, and of course not touching the bottle, effectively render this system safe. So to demonstrate the conservation of energy, all of the energy in this system is coming from a battery electrolyzing water, with in this case some sodium hydroxide electrolyte to aid in the conductivity. So there you go, you can see that the battery is supplying some 12 volts and pulling a fairly constant 5 amps, and that's generating the hydrogen and oxygen via electrolysis, and as it does so there's a small hole in the bottom of the bottle allowing the electrolyte to be pumped out by the gases generated. Now it turns out to fill this bottle I only need to turn about half a gram of water into hydrogen and oxygen, and of course when I turn it all back into water again by igniting it, all of the energy that I put into this system from this battery is released, albeit in milliseconds. Then the remote ignition is simply triggered by passing current through a bus fuse, and a few milliseconds later the entire contents of this bottle are at over 3000 degrees Kelvin, half the temperature of the surface of the sun in a pop bottle, 3000 degrees in about 3 milliseconds. So next time you pick up a laptop or a mobile phone, perceive the energy contained within these devices and the elegance of the energy stored within these systems. Now actually, much to my surprise, the bottle survived this. So what happens next? Well, you will recall that I said that to fill this bottle I only had to turn about a gram of water into hydrogen and oxygen. Now immediately after the detonation, all of that's still in the bottle, that half a gram of steam at 3000 degrees. But of course the second that comes into contact with the bottle, which weighs some 100 times as much as the steam I've generated, it heats up the bottle and softens it and cools down the steam. And after only about a second or so, the steam condenses into water, at which point the greatly softened bottle contains essentially a perfect vacuum, and so the bottle collapses, and as it does so it sucks water back into the partially melted bottle, in essence restoring the starting conditions. And so that all that's left afterwards is this twisted and melted pop bottle full of water. Anyways, I thought it was kind of a pretty way to make something that's halfway between pure beauty and hell in a pop bottle.